Hi, everyone. This is our Thermodynamics 200 coding project, which we have named Steam Turbine Turbulence.
I'm Caleb.
I'm Gabby.
And I'm Anthony, and we will be presenting this project to you. So before we begin any sort of talk about our technical report, we would like to give some group contributions. So for this code, everyone contributed very evenly to the code. So for each task, we always compared ideas and numbers to make sure everyone was on the same page. So we were always checking each other's codes and making sure that everyone was getting the same numbers. Also for this presentation, every team member contributed their own slides for this presentation and their own talking points.
This paper creates mathematical models and compares them with experimental data to evaluate specific enthalpy and entropy at the different stages of turbines. Comparing the overall turbine generator model and the data of the real turbine indicates the accuracy and performance of the models proposed. The simulation and model results find a very small error and conclude that the model simulations can be used to monitor the turbine. In the turbine being evaluated, the superheated steam enters the turbine at 535 degrees Celsius and 18.6 megapascals. Then, the cold steam exits at 351 degrees Celsius and 5.37 megapascals. The report states that the efficiency of a well-designed high-pressure turbine is about 85 to 90%, and the experimental and simulation results show that this turbine has an efficiency of 89.31%.
We were given this code that used the van der Waals equation of state to analyze a turbine. We improved upon this code, generating the Redlich-Kwong and Peng Robinson equation of state codes. Our code uses the robust Peng Robinson equation of state, accounts for changes in specific heat based on changes in temperature, calculates the temperature of isentropic operation, and the overall efficiency of the turbine. This cell initializes our conditions and important variables that we would call later in the code. We then define the volume function, which will also be used many times throughout the code. We calculate our initial volumes of the inlet and outlet states using that and the ideal volume for the argument. We calculate the change in enthalpy between ideal states and the change in the departure function also for the ideal states. We sum these three numbers together to get the total delta H of negative 9,000 joules per mole. We also do the same thing for entropy, calculating the entropy between ideal states, the departure function of entropy between ideal states. Once again, we add all three together to get the overall delta S of the system as negative 1 joules per mole. To find the isentropic final temperature, we assume the change in entropy between ideal states is 0. This code shows the calculations to find a new temperature based on that assumption. Our isentropic final temperature is 613 Kelvin. We then run through the code again, calculating new volumes, calculating a new delta H between ideal states, calculating the departure function for the enthalpy again, adding them all together to get a new delta H for the ideal conditions, which is slightly higher than the last delta H. Efficiency is the work of the real system divided by the work of the ideal system. Work is mass flow rate multiplied by delta H. Because mass flow rate would be both in the numerator and denominator, it cancels, and the efficiency simplifies to just delta H actual divided by delta H ideal. Our overall efficiency is 96.5%.
Next slide, we'll compare our numbers from the calculations we did to the literature values provided by the report. So from our calculations, as Caleb stated, it was determined that the overall efficiency of our turbine was 96% efficiency. Although, as stated earlier in our presentation, the actual efficiency from the report states that the turbine operates at around 89.3% efficiency. We believe this discrepancy is due to the actual turbine not operating at 100% adiabatic conditions. This would mean that heat would be lost to the surroundings, which would cause the overall system to be non-ideal and then less efficient. While as in our code, we assume that the system operates at 100% adiabatic conditions, which would account for the discrepancy between the efficiencies between our calculations and the report. This next slide is comparing our isentropic temperature to the actual output temperature of the system. So from our temperature calculated from the isentropic scenario is around 11 degrees C colder than the actual output of the turbine. This makes sense as the isentropic process will give the coldest temperature, while the processes that are non-ideal will have a higher temperature. This helps to further validate our results and say that they are somewhere in the right magnitude. Our last slide here is another comparison of our numbers. So as we calculated the enthalpy and entropy changes, we noticed that they had similar magnitudes as to what other classmates were calculating, and also to other literature values we found, which also helps to validate our results and say that they are at least somewhat right. Are there any questions?